Hello, I'm Julietta Gruszko from the University of North Carolina at Chapel Hill, and today I'm going to be telling you about the MAJORANA demonstrator's search for Neutrinoless double beta decay. If you've clicked on this talk, you probably already know that Neutrinoless double beta decay is a very exciting portal to beyond the standard model of physics. If we observe this, we would immediately know that lepton number is violated and that the neutrino has a non-zero Majorana mass term. So obviously it could give us insight to matter creation in the universe and to the origin of the mass of the neutrino. The experimental signature that we search for is a peak at the Q value of this decay. So a narrow peak that has width just determined by the resolution of your detector, and it sits at the endpoint of the two neutrino double beta decay standard model spectrum. So in germanium, this Q value is at 2039 keV, and here's a representation of what that resolution looks like. So the MAJORANA demonstrator is the experiment I'm going to be telling you about. We search for neutrinoless double beta decay of germanium-76 using high purity germanium detectors, and we also conduct searches for other physics beyond the standard model. We're using 30 kilograms of enriched germanium-76 detectors and another 14.4 kilograms of natural abundance detectors through most of our run. And now we're running with an additional mass of inverted coax point detectors, which I'll tell you more about in a moment. We've achieved excellent energy resolution of 2.5 keV full width half max, and we have a very low background running with these two modules in a compact graded shield with an active muon veto. And really we're relying on ultra clean materials to get to these very low background levels. So first, just to quickly talk about our experiment, I'll tell you a little bit about why we use germanium-76. This germanium is both the source and the detector, which is an advantage because it's easy to get large amounts of germanium based on the global market. This material, once you turn it into detectors, has very high purity and low intrinsic backgrounds. We're able to enrich it to 92% in germanium-76, and we really efficiently use all the enriched material, both in making the detectors and in doing our analysis. We're using this well understood technology of germanium diodes that has been around for decades. And because of these excellent detectors, we're able to get this really impressive energy resolution of 0.12% full width half max at Q beta beta, and under that, a well understood peak shape and a very linear energy scale. And all of these approaches that we take have allowed us to achieve very low backgrounds. The lowest and second lowest backgrounds of any experiment in the field have been achieved by germanium experiments. With no background lines within many full width half max of Q beta beta, a negligible two neutrino double beta decay background, and some of the very powerful background rejection techniques that I'll tell you about now. So in addition to germanium detectors, we're relying on a specific type of germanium detectors called point contact detectors. By shrinking down one of the electrodes to this very small point, you reduce the capacitance of the detector, leading to reduced noise. That lets us both push the energy thresholds of the experiments down to below a keV, letting us have an additional beyond the standard model physics program, and gives you excellent energy resolution for the double beta decay search. That point contact geometry also allows you to do multi-site event rejection based on the pulse shape. So you can see animations here of how the charge drifts in the detector once the event begins, kind of at the start of that charge line. As that charge drifts, it creates an induced induced current on your electrode and gives you a waveform that looks like this. And you can see that when you have an event that originates just at one point in the crystal, you just see a single step. And if you have events at multiple points in the crystal, this sharply peaked weighting potential here gives you a multi-step shape. And that multi-step shape is what we rely on to discriminate multi-site events. Similarly, there's very distinctive pulse shapes on the surfaces of the detector, and that lets you reject alphas and betas that are confined to the surface of the crystal. So to get the most out of these point contact detectors, we need to really actively control the backgrounds. So we do that by starting with ultra pure materials, and especially our underground electroformed copper, which has an activity below 0.1 microbecquerel per kilogram. And you can see these two references for more descriptions of that material and of our assay program. Then we machine it and clean that material in the cleanest possible way. So that means we have an underground clean room to keep that copper from being cosmogenically activated. And we go through a careful cleaning process of all of our parts, the plastics and that underground copper. And then we keep that material as clean as possible. And we do that by handling our near detector components only inside dedicated glove box and tracking the above ground exposure and limiting the above ground exposure of our germanium to prevent cosmic activation. And all of these processes rely on a parts tracking database and have a really nice result, which you can see outlined in these two papers referenced there. Once you start with these clean materials, you have to still further reduce the backgrounds. And to do that, we're relying on the fact that neutrinoless double beta decay is intrinsically single site. So in our detectors, that means that it has less than a 1 centimeter range in germanium, those betas. So you can reject anything that deposits energy further away as being a background. So our detectors here in the center are surrounded by this passive shield and then an active muon veto system. So if we see a through-going particle that deposits energy in these muon veto panels, we're able to reject that as being a muon hit. Then if you see an event that deposits energy in more than one detector, like a gamma would, that's rejected by a granularity cut. So double beta decay doesn't really escape a single detector, and so we can reject that event as well. Then finally, we apply our pulse shape discrimination. There we reject events that deposit energy at 2 well-spaced locations within the crystal, like a gamma would, and we reject surface events that are confined really only to this small insulating region of the detector, with the other surfaces being insensitive. Here's just a quick outline of our timeline as an experiment. We ran with these 2 modules for the majority of the experiment. Both of these were running, and then we stopped for some upgrades and to move things to Legend 200. So I'll tell you more about those details. So in 2020, we did an upgrade of our module 2. The goal of this was to improve our cabling and connector design and to test some things for the upcoming Legend 200. So we were able to go from 62% operational detectors before the upgrade to 100% afterwards, added some additional shielding, and started laying the ground for L200. So we removed 5 of these point contact detectors to test them in liquid argon, and installed 4 of this new geometry of detector to allow us to do low background vacuum testing before Legend 200 began. And to hear more about these new detectors and about the L200 program, I highly encourage you to take a look at Ralph Maserzik's talk here at TAUP, where he'll tell you more about Legend. Earlier this year, we finally completed our enriched germanium detector operation. So we've reached an integrated exposure of about 65 kilogram years, and then removed all those enriched detectors so that they could be installed in L200. We've continued operation in the interim with natural abundance detectors. We've consolidated everything into a single module, and we're doing background studies to keep refining our background model. In the next year, we also have some additional physics studies planned. So there's some exciting work still to come here. In the meantime, we've also worked a lot on making our analysis the best it can be. So we've made some improvements to our multi-site event rejection. Like I briefly mentioned earlier, this single step of a double beta decay like single site event can be distinguished from the multi-step like waveform that you see when you have a gamma scattering in multiple sites. And we do that based on what we call A versus E. A is the maximum value that the current or the derivative of the waveform takes on. And you can see that the ratio between this max current and the energy is very similar for every single site event. Whereas for a multi-site event, that max current value is reduced because some of the current is distributed to the second site. And this allows us to do a very powerful rejection of multi-site events. So we tune this discriminator on calibration data, and we tune it to accept 90% of known single site events. And using that, we reject over 50% of the Compton continuum near Q beta beta. So we already had A versus E in place, but we've made some improvements. We've improved the alignment of the center of the distribution that allows us to have better stability and uniformity across the detectors. We've introduced a width energy dependence correction that improves the acceptance at higher energies, making it more consistent. And we've adjusted for correlations with drift time so that the entire detector is being treated with the same acceptance and has the same width for this parameter. And that gives us a better multi-site discriminating parameter than we had before. we've made similar improvements to our surface alpha rejection. In this case, the rejection is based on delayed charge being collected late in the event from trapped charge and slow charge along this insulating surface of the detector. So once again, we tune this discriminator on thorium-228 calibration data. We accept 99% of bulk events, and we're able to reject almost all alpha events using that cut. The improvements we've recently made is that we've added transfer function deconvolution as one of the steps, and improved the alignment and the width dependence of this parameter, making a cut more consistent across the detectors. Finally, we've added, again, a drift time correction that makes the response of the parameter uniform across the entire detector. So we expect that this will provide better discrimination, but it also just provides better stability across time and across the detectors, as well as increasing our exposure. We've also made some similar improvements to our energy estimation. Our energy estimation is performed by a trapezoidal filter. We apply that to a nonlinearity waveforms that are corrected for the nonlinearity of the digitizers. And we apply a charge trapping correction that's based on a fixed time pickoff from the start of the pulse, which we call T0. This is calibrated on weekly thorium-228 data, and we can retune on the full data set once it's all complete. So some of our recent improvements here is that we've added a correction for the trigger walk that was occurring on T0. So at low energies, this T0 estimation had a bias, and by correcting for that, we've really been able to improve our linearity. Additionally, we've added a quadratic correction, which accounts for the charge recombination that occurs in the detectors. And this combination of improvements have given us a full attack max of 2.5 keV and linearity of better than 0.2 keV up to 3 MeV, as you can see here. Both of these are a record for Neutrinoless double beta decay searches, and we're very proud of the work that's gone into them. We've also been working on developing our background model further. So when we turned on MAJORANA and ran for a while, we found that instead of the predicted 2.2 counts per full attack max time year at Q beta beta, we measured a background of about 12 counts per full attack max per time per year. So we really wanted to focus on quantifying and identifying these backgrounds to make sure that we're using the cleanest possible materials in the LEGEND experiment. So one of the things that we've put some time into since then is improving our assay-based background model to reflect the as-built configuration and to reflect new assay information that we've gotten. So this is a new technique that actually incorporates the uncertainties from the assays, the masses, and the Monte Carlo, and lets you see them separately. So we've also improved quantification of the backgrounds from some of the distant vacuum hardware, as I'll speak more about in a second. And you can see that the uncertainty here is now driven by the statistical uncertainty of the lead shielding simulations, where it's very hard to get high statistics just by the nature of it. So our background at Q beta beta is estimated using this 360 keV window, excluding the peak regions that are highlighted. And our estimate has gone from about 2 counts per full attack max per ton per year to 2.9 with this new technique. That still underpredicts our observed background index though, so we still have some additional work to do. So these are some of, just a quick summary of some of those other efforts. We need some improvements to model and identify the source of the thorium excess that we're seeing. We are able to identify that it's thorium, but picking out exactly which of the hundreds of components is responsible for it is where the extra work is going in. We are conducting many more high statistic simulations to allow us to model regions that have low efficiency. So one culprit that has emerged, for instance, is this vacuum hardware all the way at the end of this cross-arm penetration that goes through the shield. The shine paths here make this background very difficult to model. We've also improved the fitting process itself. So both on the frequentist and Bayesianist side, we've changed the grouping of components and changed things like how we approach the binning and the fits to try to fit the full spectrum between 100 and 2620 keV. Finally, we're doing a lot of work on quantifying the systematic uncertainties in the background model to make sure that we understand the precision with which we're able to model our backgrounds. But ultimately, for LEGEND, one of our takeaways has been that the excess that we're seeing is definitely not from near detector components. Both multiplicity studies and the initial spectral fits support that conclusion. So our most recent result is still the 2019 Neutrinoless double beta decay result. With this result, we're looking at 26 kilogram years and reaching a double beta decay half-life limit of 2.7 times 10 to the 25th years, a little bit less than our sensitivity of 4.8 times 10 to the 25. So a new result with our combined total of 65 kilogram years is upcoming, and that will incorporate these analysis improvements I described. And there's a zoom in of that background estimation region if you're curious. Some other new results that we're very excited about. We've published the best limit on germanium-76 decay, double beta decay to excited states. Our geometry is very favorable for this because we have these closely packed detectors with no material between them. And we've been able to improve the limits on all of these processes. Finally, just a pitch for another talk at TAUP. We've done a huge range of beyond the standard model physics searches. And so if you check out Wen-Chun Su's beyond the standard model searches with the MAJORANA demonstrator experiment, you'll see new preliminary results being presented at this conference. And I'll let him speak to more details on that. So finally, we have concluded our enriched detector operation now. We started back in 2015, and now we've hit 65 kilogram years exposure with the best energy resolution and second best background of all the Neutrinoless double beta decay experiments. We are working on our background model, refining it, and continuing to investigate where that additional background that we didn't expect is coming from, and doing a bunch of analysis improvements to make this next result very powerful. Finally, we've been able to conduct all sorts of other beyond the standard model physics beyond the standard model physics measurements, which I reference you again to this talk to check out more about. And we've completed upgrades that allow us to test detectors for Legend 200, which again, if you're more curious about Legend 200, I refer you to this talk by my colleague, Ralph. So none of this work would be possible, of course, without the generous support of our funding agencies and without the work of the entire MAJORANA collaboration. Thank you for your attention.